All right, so here we need to identify each graph as either increasing or decreasing, pretty easy to do. Match each graph with its equation, maybe not quite as easy to do. And then write the constant percent change for each graph. All right, well, that won't be too hard to do either because we know that all we have to do for this one is take b minus 1 times 100%. So, first one. What's this one? Well, that's going down. So this one actually we could say is decreasing. Well, now this one going from left to right, that's increasing. Okay. Now, increasing and decreasing, what do we know? Well, looking at the b's, we know the decreasing is going to be b is less than 1, and increasing b is going to be greater than 1. So less than 1b is this one here, and so this one has to be g of x, and this one has to be f of x. Okay. And then the last thing we have to do is we have to take our b minus 1 times 100%. So we'll take 1.3 minus 1 times 100%. Well, 1.3 minus 1 is 0.3 times 100%, and that's going to give us 30%. Now this one, we're going to take 0.7 minus 1 times 100%. And here, 0.7 minus 1, that's going to give us a negative 0.3, and so that's going to give us a negative 30%. Okay, so if we look, it's increasing by the same amount it's decreasing. It's the same percentage. All right, what about the next one? Okay, well here, what we have to look at is both of these are increasing. That was easy. They're both going up as we go from left to right. Now they both have our initial point of 3. That's another thing we should probably talk about. That initial point A, that's 2, that's that point right there. This one, we have that initial point 3, and that's that point right there. Now, all that's different is the B values. We have 1.2 versus 1.4. So what do we know? Well, 1.4 is going to be a bigger change overall, and so that means this one here is going to be the g of x, and this one should be the f of x, okay? Because this one's going to change less, and so it's going to have more gradual moving up. This one's going to be steeper, and so it's going to be a bigger rate of change. Now, what is the percent change here? Constant percent change. 1.2 minus 1 times 100%. Well, that's going to be 20%. And this is going to be 1.4 minus 1 times 100%. And so that's going to give us a 40% change. Okay. So far, this is pretty easy. This one wasn't too bad. Well, this one's going to be just about as easy as that first one, because now if we're looking strictly at A's, which is all we can do, because guess what? Those are the same B's, so they have the same rate of change. We just have to figure out which one has the point where 3 is and which one has the point 2 on our y-axis. And so what can we say about them? Well, they're both increasing. And so now what we have to do is figure out which is which. So one goes through 0.3, that's this one. So this is f of x, so that means that one is g of x. And for both of them, doesn't matter which one, 1.5 minus 1 times 100%, that's going to be 50%, okay? And so that's going to be our constant percent change for both of those. So that's going to be the same percent change for both, okay? What about this one? Now we're supposed to look and see, indicate whether the function describes exponential growth or decay. So basically, is b greater than, whoops, not 0. Greater than 1, or is b less than 1? And then we find a constant percent change. All right, so how do we do that? Well, we look at that b, and we see 0.92. Well, that 0.92, that's b is less than 1. So this one is a decay. And so now if we take 0.92 minus 1 times 100%, well, that's going to give us 8%, but it's going to be a negative, okay? Because if you take that 0.92 and then subtract off your 1, you should get a negative 0.08 times 100 gives you a negative 8%. Now this one, a b is greater than 1, so we know that this is a growth. And so we say, okay, well, 1.035 minus 1 times 100%. Oops, I guess I don't need another parenthesis there. And so what does that give us? Well, that's going to be, if we subtract 1 off, move decimal, it's going to be 3.5% growth, whereas this was an 8% decay, okay? And so that's all we have to do with those. All right, so the next one, we have a labor force. So the U.S. labor force is considered to be the civilian non-institutional population 16 years old and over. In 2008, 59.5% of the women in the labor force were actively employed. The U.S. Bureau of Labor Statistics predicts that by 2016, this participation rate will be 59.2. So guess what? We're dropping. So what is the predicted change in the percent of women who are actively employed between 2008 and 2016? And what is the predicted percentage change in the percentage of women who are actively employed between 2008 and 2016? All right, so what do we have to do? Well, what we have to do is, for the first one, what's the predicted change in the percentage? Well, we're going from 59.2 down to 59.5 down to 59.2, so we've dropped 0.3%. So this is going to be a negative 0.3%. We've gone down. All right. And so now what about the next part? What is the predicted percent change in the percentage of women who are actively employed between there and there? All right, so remember, this is our X1, this is our X2. So if we take our 59.2 minus our 59.5 divided by the 59.2 and then times 100, that should give us our value. And so if we plug that in, that top is going to be a negative 0.3 divided by our 59.2 and then times our 100. That's going to give us, that'll give us a negative 0.51%. So it's going to be a 0.51% drop in the percentage of women who are actively employed. Okay, so that's the answer for part A, and that then would be our answer for part B. Okay, and so that one we just had to remember, you know, the x2 minus x1 over the x1, and it's not just that, it's the f of x2 minus the f of x1 over the f of x1, or your basically your y2 minus y1 over then again your y1. Okay, so that's how I would do that one. All right, so the next one, we're looking and we're supposed to calculate the constant percent change for the model. And then we're supposed to interpret the answer to part A in context. So we have solar power and we have sleep time for women. All right, so what do we have here first? The amount of solar power installed in the US has grown since 2000. The amount of solar power installed in the US can be modeled as M of X equals 15.45 times 1.46 to the X megawatts, where X is the number of years since 2000, and data for the years between 2000 and 2008. Okay, so that's, we know it's in that range. And so we're supposed to calculate the constant percentage change for the model. Well, what do? Well, we have to look at that B here. So that's going to be 1.46 minus 1 times 100%, and that's going to give us a 46% change. Okay, and so interpret that, you know, based on this. Well, okay, so each year there will be a 46% increase in the amount of solar power installed in the US. Okay, and so that's basically what it is, and it's for the years between 2000 to 2008. Okay, so it's going to be that increase over that period of time for each year. Now for the next one, sleep time for women. All right, so until women reach their mid-60s, they tend to get less sleep per night as they age. The average number of hours in excess of 8 hours that a woman sleeps per night can be modeled as this. And so that means they're going to have basically 10.697 hours of sleep a night, but it's going to go down based on this, okay? And so now what we have to do is we have to take 0.957 minus 1 times 100%. And so if we plug that in our calculator, we get 0.957 minus 1 times 100 is going to be a negative 4.3%. So each year, women 15 to 64 will decrease the number of hours in excess of 8 hours per night they sleep. Okay. And again, that's based on from 15 to 64. After that, it might be a different model, and so we can't really use this for those different models. All right, so what about men? Okay, so until they reach their mid-50s, they tend to get less sleep per night as they age. 20-year-old men gets approximately 8.7 hours of sleep each night. Considering 8 hours as a baseline, the 20-year-old man gets 0.7 hours of excess sleep in excess of the baseline. So basically, whereas the woman got 10.697, men are going to go only 8.7. Okay. So this amount of excess sleep decreases by 4.4% per year for men from 20 to 55. And so what we're supposed to do is model the number of hours of sleep men get per night given their age. Then according to that model, how much does a 50-year-old man get? And then after that, describe the end behavior of the model as time increases. All right, so what do we have to do? Well, thinking about what we know that, what are we going to say? How do they do it? I don't know, sleep, let's call it sleep for S of time is going to be, so S of T is equal to, well, now our baseline is 0.7 hours more. So we have to say that's our baseline. And then what we have to think about is, okay, well, we lose 4.4% per year. So what we're going to have to do is we're going to have to take that 1 minus 0.04 0.04. So we're going to have to take, let's write it down here, 1 minus 0.044. And so that's going to give us our 0.956. So we have 0.956, there is 0.957. And so then we have 0.956 raised to the x. And that should be our model for men losing sleep from 20 to the, what was it, 55, okay? So 20 to 55. Now, this is, just as the age is. And really what we need to think about is baselining this or aligning it. So this is 0, well, this means that would be 35. So really from 0 to 35 is going to be how we're looking at this, where that baseline is 20. So and the reason why we're doing that is because now we have a 50-year-old man. And so what we need to do is kind of consider, where is 50 from 20? Well, that's 30 years beyond that. And so what we're going to do is we're going to find S of 30. And so we just plug that into our calculator. So 0.7 times 0.956 to the 30. And we get 0.1814. And this is going to be hours excess of sleep. Per night. And so what does that tell us? It's going to be 8.18 hours, basically. That's what the 50-year-old man, that's how long he'll sleep. Okay. Now, so maybe we should say that's A, that's B, and so C Describe the end behavior of the model as time increases. Okay, well, basically, as we get further and further along, that excess hours are going to go to zero because it's just going to keep going farther and further and further. And eventually, if you think about how the graph of decay looks, we're going to be going, I don't know what their curve looks like, but it's going to go down here towards zero. Okay, and so we could say the limit of s of t as t approaches infinity, that's going to be equal to 0. That's going to take a while to get there. I don't know exactly how long it'll take, but it's going to get to 0 as we get closer and closer to infinity. So basically, it's decreasing without bound as x increases without bound, and basically it's just going to get to that 0 part, and we'll be done. And so that would be the end behavior. It just approaches 0 after we get further and further out from that 20-year-old. All right, so let's pause there.